We're going to run a DFS on this graph starting from vertex 1, and we're going to trace the process by building a tree. So we begin at vertex 1, and now we look at where can we visit as a neighbor of 1. 1 has three outgoing neighbors actually. It could go to 2, it could go to 3, or it could go to 5. So there's some ambiguity as to which one we should visit next, but let's just break that ambiguity and say visit vertices in increasing order. So we're going to visit 2, and then later we're going to visit 3, and then later we're going to visit 5. So first we begin by visiting 2. Now, where can we go from 2? 2 could go to 3. And where can 3 go? 3 can go to 4. Where can 4 go? Well, it could go to 2, but we visited 2 before, so we don't need to visit it again. It can't go anywhere else, so we're actually done with 4. We can back up. We were at 3. We can ask, where else can 3 go? Well, nowhere else, right? It could have gone to 4, but that was it. So now we back up again. Now we're at 2. Can 2 go anywhere else? No, it cannot. We back up again. Now we're at 1. We remembered that the 1 had 3 different out neighbors it could go to. It could go to 2, it could go to 3, or it could go to 5. Well, we already visited 2, so we visited that edge. We need to check this edge, 1 to 3. Well, we visited 3 before, so we don't need to do anything there. Now, we would try to visit its other child, which would be 5. 5 has not been visited yet, so we can add it to the tree. Now we search from 5. 5 can go to a few different places. It can go to 6, 9, or 10. As I mentioned earlier, we're going to visit these in increasing order. So we'll try to visit 6, and then later we'll try to visit 9, and then finally we'll try to visit 10. So we begin by trying to visit 6. We can do that because we have not visited it yet. Next, we would try to visit 7. We can do that. 7 has 2 out neighbors, 1 and 4. But both of these have been visited already. So we're done with 7. We can pop back up. Where else can 6 go? It can go to 8. Where can 8 go? It can go to 9. But now we're done with 9. Pop back up. Can 8 go anywhere? It can't go anywhere else, so we're done with 8. Pop back up. Can 6 go somewhere else? No. Pop back up. 5 can go to 9 or 10. So the next one we would try is 9, but we notice that 9 has been visited already, so we can't go to 9. But we can go to 10. And now 10 would try to go to 8, but we visited 8 before, so we can't do that. We pop back up. Are there any other places we could go from 5? No. Pop back up. Are there any other places we could go from 1? No. And now we're done.
This is the DFS tree for this example graph starting at vertex 1. The edges in the DFS tree are a subset of the edges of the original graph. So for example, this edge 1, 2 shows up here in the graph, but the edge 4, 2 from the graph does not show up in the DFS tree. Let me go ahead and highlight all of the edges in the DFS tree where they appear in the original graph. All of the other edges that are in the graph are what we call non-tree edges, and we can classify them into 3 different categories: forward edges, backward edges, and cross edges, based on how they line up with the DFS tree. So for example, this edge 4, 2, we can see it looks like this if we put it on the DFS tree. And we call this edge a backwards edge because it's pointing from a descendant to an ancestor. Another way of thinking about this is that 2 was visited before 4, and therefore this is pointing backwards in time. A different class of edge might be this edge 1 to 3. We can see it's pointing downwards in the DFS tree. And this is what we call a forwards edge. It's pointing from something that was visited early to something that was visited later. So it's pointing forward in time. Now, a third class of edge you might see is, for example, this edge 7 to 4. If we put this on the DFS tree, we see that it doesn't point up or down, but it points across. Neither 7 nor 4 is above the other in the DFS tree. So we call that a cross edge. There's one other cross edge in the graph. It's this one here from 10 to 8. 10 to 8. Now there's a couple other non-tree edges that we haven't considered yet. So how about this one, 5 to 9? This is a forwards edge. because 5 is above 9 in the tree. And there's one more edge that we've missed. It's this edge, 7 to 1. This is another back edge. And those are all of the non-tree edges from the original graph.
All right, so now that we've drawn this entire DFS tree resulting from running DFS on the original graph, we want to go in and classify each edge, not using a diagram, but using like actual numbers. So we're going to use visit and finish times to do this. So let's go ahead and draw the numbers, or the visit and finish times for each node respectively. So I'll go ahead and write the visit times on the left of each node and the finish time on the right side. So we visit the first node 1 at time 0. And the next node we visit is 2 at time 1. And then we visit 3 at time 2 and visit 4 at time 3. Since 4 has no out neighbors that have not been visited yet, but at this point in DFS, we go ahead and finish this node. So we finish it at time 4. And similarly, 3 doesn't have any out neighbors that have not been visited yet. So we finish 3 at time 5. And we finish 2 at time 6. And note that 1 still has 5 as an out neighbor left, so we can't finish 1 just yet. We have to go ahead and visit 5. And at this point, our visit time would be 7, because we had just finished 2 at time 6. And then we go ahead and visit 6 at time 8, visit 7 at time 9. 7 has no unvisited out neighbors, so we can finish it at time 10. 6 has 8 as an out neighbor, so we can visit it at time 11, and then visit 9 at time 12, finish 9 at time 13, and finish 8 at time 14. So now we've visited all of 6's out neighbors, so we can go ahead and finish 6 at time 15. And now we can visit 10 at time 16 and finish it at time 17. And now that we finished all of the out neighbors of 5, we can finish 5 at time 18. And at this point, we've seen every single node in the tree, so we finally finished the root node 1 at time 19. So now every node has a distinctive visit time and a finish time. And using these two numbers for each node, we can try to classify each edge as a forward edge, back edge, or tree edge. Cool. So now we have two functions that will return us the visit time and the finish time of each node. So like for some node x, for example, if it was 1, d of x would return 0, and f of x would return 19. So now that we have these two quantities for each node, we want to be able to write out inequalities such that for each edge, we can tell if that edge is a forward edge, tree edge, back edge, or cross edge. Note that we can't distinguish between forward and tree edges simply using the discover and finish times. Cool, so let's go ahead and write the equation for a forward edge or a tree edge. So if we have a forward or tree edge, we know that y is a descendant of x in the DFS tree generated by running DFS on the original graph. So in this case, we must have discovered x first, and then we must have discovered y, because we still haven't finished all of x's out neighbors. And then after visiting all of y's out neighbors, we would have finished y, and then we finally finish x. So given an arbitrary edge, if it meets this inequality using the discover and finish times, we can tell that that edge must be a forward or tree edge. Now let's think about how to write the similar inequality for back edges. Cool. So for back edges, note that x is still a descendant of y in the DFS tree, but there's an edge going from x to y. For example, all the red edges in this DFS tree are back edges. For example, 7 is a descendant of 1 in the tree, but the edge 7, 1 exists in the original graph. So we must have discovered y first. In this case, y is 1 and x is 7, if you want to look at an example. So we must have discovered y first, and then we must have discovered x. And then at some later point, we would have finished x. And we would have finally finished y. Cool. And the final type of edge we'd like to classify is the cross edge. So note that cross edges only go from like right to left, as in you can't have a cross edge from like 3 to 6. And the reason for this is if this was an edge in the original tree, 6 would have been an out neighbor of 3, and we would have visited 6 after visiting 3. So 6 would have actually been a forward or tree edge from 3, or like 3, 6 would actually be a forward or tree edge. It wouldn't be a cross edge. So since cross edges only go in this direction, we know that we must have discovered y first. So we discover y. And since x is not a descendant of y, we must have also finished y before even discovering x. Because if we had discovered x, then this would become like a forward edge. And then at some later point, we discover x, and then we finally finish x. Cool.
This is the code for DFS, where we have a visited set, which we write with x. And at the moment, this code, all it does is it visits the graph in DFS order, but it ultimately just returns the set of vertices that are visited. So at the end, if we're visiting V, then eventually we're just going to return a visited set. And that either happens here or here. Now there's two possibilities for when we're visiting a vertex. It's possible that we've visited it before. And if that's the case, then we don't need to visit it again. And so we just return the visited set that we already have. But if we actually need to visit the vertex because we haven't visited it yet, then we need to update the visited set to mark that vertex as visited. And then we need to visit all of the neighbors of that vertex. And that's what this line does. So this line says we're going to iterate over all of the neighbors of this vertex. And that's this here. We just write neighbors plus g of v. This just says in the graph G, what are all of the out neighbors of vertex V. And we're going to iterate the function DFS on graph G, which is so that's the recursive call to visit all of the neighbors of V. That eventually is going to return a visited set that's updated for all of the children, and finally we can just return that. So we want to turn this function into a more generic DFS that can do more than just return a visited set. And there's a few things that we're going to add to it in order to handle that. So what we're going to do is we're going to have a state, and we'll write it sigma. And this is something that we'll define differently for different applications where we might use DFS. So you can think, like, we're going to write it as sigma, but it has a particular type that at the moment you can think of as sort of polymorphic. And there's a few things we'd like to do with sigma. So we could, for example, visit a vertex, and we'll give it sigma, and this will pop out a new state for us. So this is saying for some arbitrary piece of data that we're keeping track of while we're running a DFS, we want to now mark a particular vertex as visited in that data somehow. We could also revisit a vertex, and we can finish a vertex. And where do we need to put these into the function over here? Well, the idea is that rather than returning just a visited set, we're going to also return a piece of state. And we're going to take that piece of state as argument. So the first thing we'd like to do is take the state, some state parameter as input, and then we also want to return it when we're done. So we can do that here by in the case where we've already visited the vertex previously, we don't change the state. But now, if we actually need to visit a vertex, we can do that by updating the state, by visiting that vertex. And now when we iterate over all of the neighbors, we have to iterate the state parameter as well. And we can do this by just making sure that we change what the initial value is that we pass to the recursive calls. sigma prime is the new value. Let me make some more space. And then the thing I just erased. We need to update this here. So we pass in a state value, and we get out a final state value for this. So this is going to give us back a sigma double prime, and then the x double prime, the visited set. And finally, we just have to return the final state value together with the final visited set. So I made a couple mistakes. I missed the revisit and the finish. So we saw that we can update the state by visiting a vertex, but we can also update the state by revisiting and by finishing a vertex. Those are the other two things I mentioned. And they go here and here. So let me rewrite those. In the case where we've previously already visited a vertex, we can mark that in the state somehow that we're revisiting a vertex a second time. And we will see some examples where that's useful. And finally, down here, we'd like to mark a vertex as finished, and we can do that by calling the finish function where we pass in this final state value. And that will update the state one more time, and that's the thing we will actually return when the DFS completes. So let's do a small example where we use this generic DFS in order to do a particular application. And the thing we'd like to do is to annotate each vertex with its visit time and its finish time. In order to do this, we can just ask how we define this state parameter and how we update it when we are running the generic DFS. So how can we do visit and finish times? Let's define the state to be two lookup tables. One of them is going to be a lookup table for the discover time, and one of them is going to be a lookup table for the finish time. So both of these are going to be mappings of vertices to times. And we just have two of them. And we'll just implement times as integers. Right? This is just an integer. And now we can ask, how do we implement these different functions? So now a state is going to be a tuple, and we can write it as, let's say, we'll use the variables d and f for the discover time mapping and the finish time mapping. And so when we visit a vertex, we just have to update when it was discovered. So this is going to be d union the mapping v points to. We're missing something, right? What do we put here? We don't have an input to the function that tells us the current time. So we need one more piece to our puzzle, and that's going to be the current time. And this is also an integer, right? This is an integer. So we take three things as a state parameter. Let's say C for current time. And when we want to visit a vertex, what we do is we update the discover time by mapping V to the current time. We don't have to update any finish times. And now we want to increment the current time because we visited one thing. So where does this get called in the code? It gets called here. So you can imagine when we need to visit a vertex, this will update the current time and mark v as having that previous current time. The revisit function doesn't need to do anything. So if we take some dfc and some vertex, well, actually, we just return the same values. Revisiting a vertex doesn't change the timestamps, and it doesn't change the discover or finish times of any vertices. But the last interesting thing is the finish time. So if we take this triple, dfc, and we want to finish a particular vertex, we can do that sort of symmetric to this one. We leave d unchanged, but now we update f by including the mapping v points to the current time, and we increment the counter. This gets called here. When we finish a vertex, you can imagine that if we trace through here, you update the timestamp here, and then you do this iterate over your children. That updates the timestamp many times, potentially. Finally, we get here, and we update the timestamp one more time, and we mark v as finished. The last thing we should ask, actually, there's still one piece we're missing, which is what's the initial value that we pass in when we call DFS? So we've defined how to update it, but we don't actually know how to start. So you can imagine we have some initial values. Let's call it sigma 0. This is some d0, f0, c0. Initial values of these state parameters. Well, we can just define this to be empty mappings for d and f, and the initial timestamp is 0. So now if I call DFS, where initially I pass sigma 0 there, and I pass the empty set as my initial visited set, this will produce all of the visit and finish times for every vertex. So now let's do another example of using generic DFS. And in this example, what we're going to do is we're going to annotate each vertex with its parent in the DFS tree. And once again, what we need to do is we need to define what the state parameter looks like and how we update it when we visit vertices, revisit them, and finish them. So the goal is to get a mapping which takes each vertex to its parent. Okay. Now there's one special vertex in the graph which doesn't have a parent, and that's the root of the DFS. It's the source of the DFS. So what we're going to do in that case is just map it to some none value. And let's just write that with a dot. So the root we're going to map to this dot. You can implement this in standard ML with a sum or a none, where here we're doing like some parent, and here we're doing none. That's one idea, or there are many different ways you could do this. So this mapping is going to be a part of our state parameter. But we're actually going to need another piece of data, which is going to be a stack of parents. And we'll see how this works when we actually walk through the code. But what we're going to have is a parent stack. And we're going to have this vertex to parent mapping.
Sam, I have a question.
Yeah, Anish, what's your question?
So why do we have to use a stack? Why can't we just store like the current vertex or something?
That's a great question, Anish. Thanks for asking it. Let's try that. So rather than using a stack, let's try to just use a single vertex. So the idea is we're going to just try to store what's the current parent, and we're going to update that as we go along, and we'll use that to update the vertex to parent mapping. So let's give it a try. Visit works, because what we can do is, if this is the current parent, here I'll write it with a little p, and this is the lookup table for the other parents. And if we want to visit some vertex, well, this is easy. What do? We update the lookup table so that the parent of v is that current parent. And then what is the next parent going to be? So after we visit v, we then are going to visit all of the children of v. And each of those children has v as its parent, so we can actually just update the current parent to be v. So this seems like it's going to work. Once again, revisit isn't going to do anything interesting. To define finish, it turns out actually we do have enough information to define finish. We can use t. So in this case, if we want to finish a vertex, all we have to do is update the current parent to be the parent of that vertex, which is in t. So this is going to be t at v. And we don't have to actually update t when we return. And then finally, we just have to define this initial state value. So this is going to be a dot to mark the root with the correct parent, and an empty mapping. So this is an alternative way of doing the vertex to parent mapping, where we don't use a stack, but instead actually just look up values in t.
We will now use a stack of parents to solve the same problem and implement the visit, revisit, and finish functions with this new data type.
In order to see how the parent stack works, it might be helpful to look at the visit function first. So we have a parent stack, and we have a, let me actually write this with, oh, damn, it doesn't actually. Okay, let me write this with a P, and this lookup table for the parents we'll write with a T. When we want to visit a particular vertex, we're going to look at the top value on the parent stack and use that as the parent for this vertex. Is this the correct thing? Yeah. So imagine we implement the parent stack with a list of vertices. Think of this as a vertex list. Then if we look at the top value, this little p, on the parent stack, we can use that p as the parent of v. What we're going to do is we're going to update the lookup table with v points to p as its parent. But we actually need to also update the parent stack, because this is going to get passed to the children. And if we look at the code, first we visit that vertex, and then we use this new state parameter to visit all of the children. Well, when we visit the children have v as their parent. And so this is why we're using a stack. So we're going to push v onto the parent stack. The new parent stack is going to be v first, and then that previous parent, and then finally the rest of the parents. So each of the children will see v as their parent. But when we actually did v, we saw p as the parent. OK. So next, it might be useful to look at how we finish a vertex. When we get back through iterating over all of the children, what we need to do is pop from the parent stack. So here, if we see when we get to finishing a vertex, we should assume that we get back the same state that we originally gave to the children. And this is what we need to guarantee when we implement finish, is that we return to the previous state that we saw before. And the way we can do that is by popping one thing off of the stack. So we're going to pop v off the stack and return to what the state looked like when we first entered the function. When we revisit a vertex, we don't have to do anything. So you can see here, revisit, we can just return the same values that we got in. And the last thing we have to ask is, what are the initial values that we pass in here when we call DFS for the source vertex? So I mentioned that we were going to map the roots to this special like none value, which we mark with a dot. So our initial parent stack is going to be a singleton list with the dot. And initially we have an empty mapping for the vertex to parent mapping. And with this code, if we run generic DFS and we look at the final value of t, it will tell us the mapping of each vertex to its parent.
Woo! All right. So we're going to go over a quick aside about the bigger picture in 210. So when we implemented, or when we taught you about scan, we asked you to basically intelligently pick an associative function, f, that tries to solve the problem you're working on using contraction. And since scan is parallel, we don't really need to care about how scan works under the hood when we're picking this associative function f. And you use this when you were solving Skyline Lab. For augmented tables, we asked you to pick an identity function and also, more importantly, an intelligent reduce val function. And we don't really care about how the augmentation works under the hood, but this reduce val function allows us to solve bigger and more complex problems using a simple approach. And you probably used this when you were solving Range Lab. And the last one, which we just learned about, is generic DFS. And in generic DFS, we ask you to intelligently pick a data type, sigma, to solve your problem. And also, we ask you to implement 3 functions: visit, revisit, and finish. And by implementing these 3 functions alongside the data type that you pick, you can solve a lot more complex problems without really worrying about what order you visit the vertexes in or how you go about visiting the entire graph. Just by implementing these 3 functions, you can solve a much more complex problem.
Okay, so now we're going to do a BFS search. It's similar to a DFS search, and we're going to create a BFS search tree here on the right. So the difference between a BFS search and a DFS search is that we can explore all the neighbors of the current vertex that we're looking at in parallel in the BFS search. So we're going to do that layer by layer in the tree. You can imagine each layer to be a k number of hops from the source node that you're looking at. So for example, if 1 hop away from the vertex 1 would just be the children of 1, and 2 hops would be the children of those children, and so on and so forth. So we're going to start at vertex 1 at the top. That's going to be the root of our BFS tree. And we're going to discover its 2 neighbors, or its 2 children, which are 2 and 5. So I'm just going to mark those edges as discovered. Okay, so then in the next layer, we're going to look at the children of 2 and 5. So 2 has 4 children, 0, 3, 5, and 4. We're going to discover those at the same time. 0, 3. 5 is already discovered, so we're going to label that as a non-tree edge. 0, 3, 5, and 4. Cool. And now we're going to look at the children of 5. So 5 has, let's see, 1 child, which is 3. And since 3 is already discovered, that's going to be another non-tree edge. Great. Now for the next layer, what's left to look at is the children of 0, 3, and 4. So let's start with 0. The children of 0 are 2 and 1. Notice that those are both discovered, so those are 2 more non-tree edges. The children of 3 are 1 and 4, also discovered. And then finally, the children of 4, 4 has no children. So this is our final BFS tree. And yeah. Okay, so now we're going to go over the code for BFS. Let's take a look over here. So first we define a wrapper function, BFS up here, and then we create a smaller function, BFS prime, that's going to take in some sequence of, they're going to be vertex options, And we're going to denote a vertex like this, or a vertex option like this, where this represents none, and this represents sum of an integer, or which is the vertex. And then f of I, which is going to be our frontier. So if our frontier is empty, that means we have nothing else to discover. So we're just going to return the sequence. Otherwise, we're going to create the neighbors of all the elements in our frontier. So for every vertex inside of the frontier, what we're going to do is we're going to find their neighbors in the graph G that's passed in to the original function. We're going to map each child to the parent, and then we're going to filter out for the ones that haven't been discovered yet. Remember, x of I represents all the elements that have been represented or been discovered or not, based on whether it's a none or sum of the vertex. Okay, so now if you think about this for a second, what if you have two vertices in the frontier that discover the same vertex? Well, then you're going to have duplicates in here. So now what we need to do is we need to deduplicate all of these. So what we're going to do is we're going to inject all of these elements inside of the x of I that we passed in. So now all of these are going to be filled in with the new elements that we just discovered. And then what we're going to do is we're going to filter out for each of these elements. What we're going to do is we're going to look at each pairing of the child to the parent inside of this neighborhood set we created, such that the pairing is also matched inside of this this I plus 1, this new set that represents the vertices that we discovered. This way, we can get rid of the duplicates that were just created inside of this set. Cool. Now all we do is just recall recursively the function BFS prime on the new set that we created and the new frontier. So now, what do we call BFS prime initially on? Well, we need to initialize x of I, or we need to create our init array for x of I. So the init array is going to just be a bunch of nones for all the vertices in G. Then we're going to update one of these elements for the root, or for the initial element that we're looking at. So we're going to update s, which is passed in here, to be the int option s. And our frontier initially is just going to be the root. So we're going to pass that into BFS prime, and then the function should run from there. Okay. So now we're going to do an example with this code. So using this graph from earlier, we're going to run with the code and see what it looks like. So we have the initial line over here, which represents the root inside of the frontier and the root inside of x of I, and then the neighborhood of the root. So if you look here, 1 has a neighbor of 2 and a neighbor of 5. So the child 2 maps to its parent 1, and the child 5 maps to its parent 1. Okay, so now if we take a look at the code, we're going to inject into x of I. So we're injecting 2 and 5 into x of I. So that's going to look like the following. 1, 2, 3, 4, and 5. Okay, I made a small mistake here. So actually, inside of these boxes, we want to put down the parent of the vertex, not the vertex itself. So what we're going to actually map these to is 1 and 1. Great. So what is our new frontier? Well, our frontier is going to be all the vertices that we just discovered, which is going to be 2 and 5. And now we need to look at the neighborhood of the frontier. So if we look over here, 2 has 4 children. So it's going to be 0, 0, 3, 4, 5. And then 5 has 1 child, which is 3. But we already discovered 5, so that's not going to be in our neighborhood. So it's going to look like this. So we have 0, whose parent is going to be 2. Then we have 3, whose parent is going to be 2. Then we have 5, which we already discovered. So if you recall in the filter, we have all x of i's that are none. Since this is not none, we're not going to include it. So 5 is not going to be in there. Then we have 4, which maps to 2. And then now we look at the children of 5, and that's 3. And 3 maps to 5. Okay. So notice we have a duplicate here. Both 2 and 5 discover 3. But inject will just take one of those and update the sequence. So if we move on here, down here, we're going to update all the parents. So 0 has a parent of 2. These remain the same. 3 has a parent of either 2 or 5. You could just pick one. So depending on your implementation of inject, it'll pick one, so I'll just pick 2. Then we have 4 is 2. And then 5 is just going to be 1. Cool. So our new frontier is going to be all the vertices that we just discovered. So that's going to be 0, 3, 4. And then the neighborhood of the frontier, well, let's take a look. So 0's neighbors are 1 and 2, which are already discovered. Well, everything's already discovered if you look at the set here. So our frontier is going to be empty, because in this filter, we're going to just get rid of it. So this neighborhood is just going to be empty. Okay, cool. Now, if we do the next run, we're not going to update anything. So we're just going to have 2, 1, 1, 2, 2, 1. Our frontier is going to be empty because we had nothing to update. Therefore, our neighborhood is empty. And now this hits our base case here. If f of I equals 0, or the length of f of I equals 0, then we stop, and then we're done. Cool.
All right, now we're going to analyze the cost of BFS, and we'd like to figure out its work and span. And you might ask, how do we approach this problem? So we can see that BFS runs in rounds. Where first we have a source vertex, and then we have all of the vertices that are reachable from one hop away from the source, and then all of the vertices that are reachable 2 hops from the source, and so on and so on. So this is going to continue until we visit every vertex in the graph. And one strategy we might use to analyze the cost then is to sum up the cost on each round, and then just sum over all of the rounds. So how long does this go? I mean, how many rounds are there in a BFS? Well, clearly there can't be more than n rounds in a BFS, because we're going to visit at least one new vertex on each round. But n seems like too loose of a bound. We're probably going to visit a lot of vertices on each round, and so we're going to have much fewer than n rounds. So we actually introduce a new parameter in order to talk about the depth of the DFS, like how many rounds there are. We call this the diameter of the graph. And we're going to write that with a little d. And this is the number of rounds of the BFS. It's also another way of thinking about the diameter is it's the length of the longest shortest path. So amongst all the shortest paths in the graph, it's the length of the one that is the longest. So that's going to be there's going to be some vertex down here, which is furthest from the source. And however many hops it takes to get to that vertex, that's the diameter of the graph. So we're going to try to state the cost bounds of BFS in terms of this diameter, and then also in terms of the number of vertices and edges in the graph. So coming back, how much work do we do per round? So let's imagine we're somewhere in the middle of a BFS. And on a particular round, we have some frontier, I, and then all of these edges are the neighbors on that round. So right here, when we construct this ni, it's all of the out edges from that frontier. How much work do we need in order to construct ni? Well, for each vertex in the current frontier, what we're going to do is build the set of its out neighbors. Okay. So we could write, let's see. We have to, what's a good way of describing this? Yeah. The work of constructing this sequence, well, we can calculate that just by looking at the size of this sequence, because each element is first, we're going to tabulate these inner sequences, okay, and filter them. So we're paying linear per element of the final sequence. And then we flatten, so we pay still linear per element of the final sequence. And the question is, how big is this sequence? Well, we're actually going to introduce a new notation, and we'll come back to this. But let's write double bar fi is going to be the sum over vertices in that frontier of 1 plus the degree of the vertex. So this is actually the cost of constructing Ni asymptotically. We pay at least 1 to consider each vertex in the current frontier. And then additionally, for all of the out edges coming out of that frontier, we have to pay for those as well. And we can do that by summing the degrees of all the vertices that are in the frontier. This is the out degree of this vertex. So all of the vertices that are one hop away from that vertex. You might wonder that it seems like there's some sort of double counting happening inside of this summation, because if we have, for example, 2 edges, you could have like 2 different vertices in this frontier, but both of them have an out edge that points to the same place. We're going to count both of those edges in this summation. And you can think about it as counting edges, not vertices. And that's going to come back to later. We're going to be adding these up, and we'll see that we can write that in terms of m, not n, in terms of the number of edges and not the number of vertices. Good. So this is, asymptotically, this is the cost of constructing that Ni. Okay. So what other costs do we have on a round? Well, we have to do this inject. The inject is going to pay, once again, at least 1 for each update. We're just counting work here. So we're going to pay for the size of Ni. Well, the size of Ni is going to be the sum size of Ni is equal to just the sum over V in the current frontier of just the out degree. Right. So the cost of the inject, well, we're going to pay linear in the number of vertices in order to copy this value of xi, but we then pay the size of Ni in order to do the injection. Okay. And the last step here is to do this filtering. So this is also going to be linear in the size of Ni. Because all we're doing is, this is like a constant time check to look up whether or not a vertex has been visited in this round. And so this is going to be just a filter over Ni. It's also a map kind of baked into it, but that's still just a linear cost in the size of Ni. Good, so that is one round. One round is going to cost this double bar is Fi plus the size of Ni. And this is the work on round I. As I mentioned before, the goal now is to just sum this up over all rounds. And we have, so now if we can, now we can ask what's the total work. And this is going to be just a summation over rounds I of the work at round I, which in this case is just going to be a summation of these. So how do we proceed from here? We're looking at sums of degrees over many rounds. Well, let's make some observations here. Do we ever visit the same vertex twice? Or another way of asking this is, these v's inside of each fi, do you ever see the same v appear twice? Like is there say like an f1 and then later like an f10 where you see v appear in this frontier and you see the same v appear in that frontier? No. You can't see this happen because we only visit each vertex once. So that means that we can actually rewrite this expression as a summation over all vertices in the graph of 1 plus the degree of that vertex, where I'm double counting here. So let's do this asymptotically. The reason I introduced doing asymptotic just because there's like some redundancy here in these two, because we're ultimately just summing degrees. So we can kind of simplify this by just saying that asymptotically we only care about this double bar fi. And now we've rewritten it, rather than summing over rounds, what we're going to do is we're going to actually just sum over all vertices in the graph. And then the result is that each vertex is counted once here, and then each edge is counted once here. So this is going to come out asymptotically to n plus m for the work. So the work of BFS is actually just linear in the number of vertices and edges in the graph. So now we're going to consider the span of BFS. And as I mentioned before, BFS operates in rounds, and the number of rounds are the diameter of the graph. So we're going to be looking at summing over rounds, and the number of rounds is d, the diameter. How much span do we have on each round? Well, let's break up this into multiple parts. So first we look at this big thing for constructing ni. We have essentially a big tabulate, and then a filter on each of these inner sequences, and finally a map. So the tabulate is going to be constant span. The inner filters are going to be logarithmic span. And now I'm ignoring some details here as to like the specific sizes. We're actually just going to say log n, because that's a good enough bound for what we're interested in improving today. So we can bound the cost of these inner filters by log n span. And then ultimately the flatten is going to be on something which potentially is this big, but that can't be larger than the number of edges in the graph. It could be as big as log m span for a single round. But as we've seen before, we know that m is going to be at most n squared. And so we can then see that asymptotically, something which is O of log m is actually O of log n. And this lets us simplify the span of that first line, constructing the set of out neighbors, to be O of log n. Now, what are the other costs on one round? We have to do an inject. And depending on your implementation of inject, whether it's non-deterministic or if it's deterministic, you might see either constant span here, or you might see some sort of logarithmic span. But we can bound it by log n span in the same way, because we know that this thing can't be larger than m in size. And so we could see up to log m cost here in order to do the inject if you wanted to do, say, a deterministic inject. Finally, to build the next frontier, this is just going to be a filter and a map over ni. So once again, we're going to see a log m in the span for the same reason. The filter pays logarithmic, And the size that we're dealing here with is up to size m. So the span for one round asymptotically is log m. And once again, we can write that as log n, based on this reasoning that m can't be larger than n squared. And how many rounds do we have? We have d rounds. So the total span we can write as summation over round number I of this log n, which is the span on round I. And this gets us asymptotically d log n for the span.